So this video is about the generation of a wideband FM signal by using an indirect method. So that indirect method is called the Armstrong's indirect method. So in this method, as we expect, we first generate a narrowband FM. This narrowband FM is then converted into a wideband FM using frequency multipliers. So how can we realize a frequency multiplier? A frequency multiplier is basically a nonlinear device that is followed by a band pass filter. So to explain the frequency multiplication process, let's look at a nonlinear device whose output is yt for an input of xt. So let's say the expression for a nonlinear device is given by this equation, where we have a2 as some constant of this nonlinear device, and the function that this device performs is that it takes the square of the input signal, which is xt. So let's say if this xt is an FM signal. So we know from previous knowledge that the expression for an FM signal is equal to, like, let's say if xt is an FM signal, so this would be equal to a cos, we have omega ct plus kf, the constant, FM constant, minus infinity to t. We have an integral of the baseband signal, right? So this is the expression for an FM signal. Now let's substitute this expression in place of xt. So what we get is this equation. The output yt is given by this expression, where you can see a2 appears, the constant appears as it is, and we take the square of xt, so which becomes cos squared, and the term inside represents the phase of the FM signal. Now, by using a trigonometric identity, such as, let's say we have cos squared theta, we have this trigonometric identity, 1 plus cos 2 theta divided by 2. We use that identity and we are left with this signal. So if you look at this signal, we have frequency of 2 mega C here, right? And also the deviation has been multiplied by 2. So that means after passing a narrowband FM signal through a nonlinear device, we can change, or we can increase the frequency and the deviation of that FM signal. So if we use a band pass filter that is centered at 2 mega C, we can recover our FM signal from this. So this is the way we can use a nonlinear device to multiply the frequency of narrowband FM to obtain wideband FM. Because it's wideband, because not only the frequency, but the deviation is also multiplied by 2, or whatever nonlinear factor we have. So let's generalize this nonlinear device. Let's say it has a characteristic of this. So the yt is equal to a0, a1 xt, a2 x squared t, and so on. So it depends upon what kind of a nonlinear device we are using. Now, if we perform the same function that we did here, we replace this xt with a narrowband FM signal. What we get on the next slide is, so we have replaced this xt with the narrowband FM signal, and this is what we obtain. So the constants are now C0, C1, C2 because of the product of A, which is the amplitude of the narrowband FM, and the product of the previous constants of the nonlinear device. So the new constants that we are getting is C0, C1, and so on. And similarly, the terms, the rest of the cosine terms that we obtain are shown here. So this is for linear function, linear xt that we see here. For x squared t, as before, we know it becomes 2 omega c plus 2 kf, and integral of m alpha. or the integral of the baseband signal, and this continues depending upon the type of nonlinear device we have. So it can go up to n omega c and n times the frequency deviation. So the output will have all the spectrum at the output will have all these frequencies, and it will have, and all these frequencies will have all these deviations. So each one of these components is an FM signal separated from the other. So it depends which one we want. We can use a band pass filter, let's say, to filter out 3 omega c, 4 omega c, which will have a respective frequency deviation of 3 delta f or 4 delta f. So a band pass filter centering at n omega c can recover the FM signal, whose instantaneous frequency has been multiplied by a factor of n. So the deviation also increases, and the frequency also increases. So these devices consisting of nonlinearity and bandpass filters are known as frequency multipliers. So we can obtain a wideband FM by using frequency multipliers whose input is narrowband FM. So an issue with frequency multiplier is that it increases both the carrier as well as the frequency deviation by an integer n. So we may not require this in all the cases. So let's say if we want a 12-fold increase in the frequency deviation, which is delta f, right? If you want to increase this delta f 12 times, we can use a 12th order nonlinear device or 2 second order and 1 third order device, right? So they can be used in cascade. So the output has a bandpass filter centered at 12 omega c, resulting in a signal whose carrier frequency and the frequency deviation is also 12 times of the original value, right? So this forms the basis of the Armstrong indirect frequency modulator. So we first generate a narrowband FM approximately, and then multiply this narrowband FM, the frequency, and limit the amplitude variation. So there could be a scenario where we want to multiply the carrier frequency, but we want to limit the delta F. You do not want the delta F to increase accordingly. So, and we can have the other case as well. So we may want to increase delta F, but we want to keep the carrier frequency same. So frequency multiplier, what it does is it multiplies both of them. So generally what we require is to increase delta F by a very large factor, which is, let's say, n. This increases the carrier frequency by n as well. So such a large increase in carrier frequency may not be needed. So in this case, we have to, use another type of component, which is called the frequency mixer, as we have studied before. So what it does is, if we have used a frequency multiplier, it will increase both NFC and it will also increase N delta F. So to bring this down to a suitable value, we can then use a frequency mixer to shift down the carrier frequency to our desired value, right? So this Armstrong transmitter indirect method is shown in this block diagram, where you can see we have from the left, if we start from the left, we have MT, we take the integral of MT, so we get AT. This integral is used in a double sideband suppressed carrier modulator to generate a narrowband FM signal here. At this point, we have a narrowband FM signal where we have, let's say, a local oscillator. We have a crystal oscillator of 200 kilohertz. The output is a cosine wave. We shift the phase of this and we get an output of minus A sine omega CT. So we do this because if you remember in the expression for narrowband FM, it's the same as the double sideband suppressed carrier expression, but the only difference is that the second term in the equation is shifted in phase, as if we compare it with the AM signal. So narrowband FM has a shifted carrier in the expression. So this way we get narrowband FM. Now we want to multiply the frequency. So let's say we multiply it by 64. So at this point, the carrier frequency is 200 kilohertz. The deviation is 25 hertz. When we multiply it with 64, we get a carrier frequency of 12.8 and the deviation becomes 1.6 kilohertz. Now let's say we do not want such a high carrier frequency. Let's say at the end, we want to get a carrier frequency of 91.2 megahertz and a deviation of 76.8 kilohertz. So if we multiply this signal with 48 to get a deviation of 76.8, so in that case, the carrier frequency would also be multiplied and we would get a very high value, which is not what we want. So at this point, we use a frequency, as we mentioned here, we use a frequency mixer to reduce the frequency of the carrier. So in this case, the local oscillator used is 10.9 megahertz. When we multiply them at the frequency mixer, we can then get, we can translate the frequency of the input to this point. Remember, frequency mixer does not affect the deviation of the input. So that remains the same. It only changes the carrier frequency. So that has been brought down to a lower frequency of 1.9 megahertz. After this, if you multiply it with the frequency multiplier, as before, we can get our desired FM signal, which is now a wideband FM signal. So this is a wideband FM. We can then use a power amplifier and then transmit it through the antenna. So just to discuss all this block diagram, this process, so the final output required is a carrier frequency of 91.2 and a frequency deviation of 75 kilohertz. Let's say this is the final output required. We start with a narrowband FM signal that has a carrier frequency of 200 kilohertz. It's generated by a local oscillator, a crystal oscillator, as we saw. This frequency is generally used because crystal oscillators at this frequency are quite stable. So they are stable to construct. So we start with this carrier frequency because if we start with a stable frequency, the end frequency would also be stable. But if this frequency has some deviations, that deviation would be multiplied at the output of the Armstrong modulator, the FM generator. So then we maintain, let's say, a beta of much less than 1, which is required for narrowband FM. Beta is the sort of modulation index for FM, and it's equal to basically the frequency deviation divided by the bandwidth. Now, if we are using tone modulation, instead of bandwidth, we can use the maximum frequency of the baseband signal. So for tone modulation means that in place of MT, which is the baseband signal, we are using a carrier, we are using a sinusoidal signal. So just to perform calculations, and in that case, beta would be delta F by Fm. So let's say the deviation we choose is 25. So we want to start with a smaller deviation. Now, baseband spectrum, this MT, if we want to have a high fidelity baseband signal, the range of frequencies that it can have generally is between 50 to 15 kilohertz. So the choice of 25 hertz is reasonable in this case. The choice of 25 hertz for delta F is reasonable because that will give us a beta of 0.5. So we want to satisfy this condition because it is required for narrowband FM. Now, what if our baseband signal is at 50 hertz? Then it would be quite difficult to get this condition, like beta much less than 1. So in that case, we have to choose a suitable value of delta F, which is in the numerator. So let's say if we choose 25, so the lowest value of beta that we can get is the maximum value of beta that we can get is 0.5. And this is the worst case scenario when FM is 50. So for higher values of baseband spectrum, this beta can be much less than 0.5, and so this condition is more and so satisfied more easily, right? So in summary, the issue we have here is we want to satisfy this condition, beta much less than 1, which is for narrowband FM or narrowband PM. So that to satisfy this condition becomes difficult at low frequencies of the baseband signal. Let's say if you have a 50 hertz signal, because we cannot reduce delta F more than 25, the deviation. If it's less than this, then it would be difficult to, multiply this. Then we would require many multipliers to get a higher frequency deviation that we want at the output of the Armstrong modulation. So I hope this point is clear. Now to achieve delta F of 75 kilohertz, remember we start with 25 and we want to achieve 75 kilohertz. The multiplication factor is around 3000, right? Which is in fact equal to 3000 because 75 is the output, 25 hertz is the start. So when we divide this, we get a multiplication factor of 3000. This can be obtained, as we saw in the block diagram, in two stages. First, we have 64. We multiply it with 64. Then we multiply it with 48. So the total multiplication factor we obtain is 3072. So that gives us a frequency deviation of 76.8. So this is not exactly equal to 75, but it's quite close to 75. If we want to get it exactly equal to 75, then we have to reduce delta F. We have to reduce that delta F from 25 that we saw here. We have to reduce it from 25 to, let's say, this 75 divided by 76.8, which is what we obtain through normal multiplication. So we get 24.41. So if we start with this frequency, if we start with this delta F, then multiplying it with 64 multiplied by 48 will give us a deviation exactly equal to 75. So this is how we can adjust. So multiplication is implemented by using frequency doublers and triplets, as discussed before. So multiplication of 64 can be obtained by 6 doublers. So that will give us 2 raised to power 6. And then we can have a multiplication of 48 as well. This can be obtained by 4 doublers. So let's say we have 2 raised to power 4 multiplied by a tripler into 3. So that gives us 48. The multiplication of FC by the carrier frequency that we have at the beginning, the narrowband carrier frequency, if you multiply it with 3072, we would yield a final carrier of 600 megahertz, which is not what we want. We want a final carrier of around 91.2 megahertz. So that's why, as discussed before, we use a frequency translation stage in between. And that translation has been performed as discussed before, this has been performed to reduce the frequency in between. So this problem is solved by frequency translation. First, multiplication by 64 results in a carrier of 12.8 megahertz. So the deviation becomes 1.6 kilohertz. Now we use a frequency mixer. So that has a carrier frequency of 10.9 megahertz. So we subtract 10.9 from this through the mixing process. This will shift the spectrum to 1.9 megahertz. The deviation remains as it is. It does not, the mixer does not change the deviation. So frequency converter shifts the entire spectrum without altering delta F. Hence, delta F remains the same as before. So at this point, as we saw in the block diagram, we multiply. We use a multiplication of 48. That gives us a carrier frequency of 91.2, the desired carrier frequency, and the desired frequency deviation. So the advantage of this scheme is frequency stability, because we can start with a low frequency, which is stable, and at the output, the frequency remains stable. But there's an inherent issue of noise in this technique because the use of so many multipliers each of the multiplier adds noise, and that noise is multiplied throughout these different stages of the Armstrong indirect method of generating wideband FM.